Hi, my name is Dylan, and this is the presentation of my group's project, Diffraction Patterns of Red and Green Light. It's by Sean Emmons, Kathy Serrano, Sam Shaner, Dylan Palmer, and Ashley Spires. Before we get into our project, you need a little background on wavelength and diffraction. Wavelength is most easily explained in relation to the visible spectrum of light. There are many different wavelengths, and each one corresponds to a different color of light. For this project, we used red and green, which will have wavelengths of 700 and 550 nm respectively. Now diffraction is when a beam of light, or in our case red and green lasers, spreads out after passing through a narrow space or along an edge. For our project, we use a device that will create two small openings that will create a pattern of light that corresponds to its wavelength. The patterns of diffraction and wavelength of the light making them are directly proportional. When wavelength increases, so does the magnitude of diffraction. When it decreases, so does the magnitude of diffraction. And that is what this project aims to prove. Now the most important part of our experiment is its equation, because this is what's going to allow us to prove that the wavelength correctly corresponds to the diffraction it's making. So the equation that we're using is delta y equals lambda times L over D, where lambda is the wavelength, L is the distance from the viewing screen, and D is the distance between the slits of the device. So we used red and green lasers. First, we tested our green laser. We have two values over in the top left here, where A is the slit width in millimeters, and D is the slit separation in millimeters. The distance to the laser from the laser to surface with pattern is 1.606 meters. And the spacing between bright fringes in this center is 1.7 millimeters. For our red light, the slits are the same. The distance from the laser to the surface with pattern is 1.606, and the spacing between the bright fringes in the center is 2.1 millimeters. Looking at the picture in the bottom here, you see there's one bright fringe in the middle, and then two other slightly less fringes off to the right and left. You can see the distance between them is much larger than it was if you look over here at the green pattern, where there's one large fringe in the middle and two very much smaller ones to the right and left. So moving to our calculations with the green laser, looking back at our equation, we used 0.0017 meters times 0.005 meters over 1.606 meters. That gave us 5.29 to the 10⁻⁷ also known as 529 nm. So the wavelength that we calculated was 525 nm, and the bright fringe spacing was 1.7 millimeters. If you do lambda over delta y, you get 311. Now the assumed and accepted wavelength for green light is 550 nm. So there was some error here, but we did receive the same wavelength with our calculations each time we did a trial with the green light. Moving to the red laser, we had 0.0021 meters over 0.0005 meters divided by 1.606. That gave us 6.53 times 10⁻⁷, or 654. So the wavelength we calculated for the red laser was 654 as opposed to the 700. So we did calculate low on both of our lights, but like I said, we still got the same wavelength through our trials. So there's a source of error there that we haven't identified that we would probably like to fix if we were to continue working on this project and just lowering that that percent error. So the wavelength for red laser based on our calculations was 654 nm, and the bright fringe spacing for this one was 2.1. And if you divide those, you see that you still get that 311 difference. So the difference between the two is the same for both the red and the green, but that's because as the wavelength went up, so did the fringe spacing at the exact same amount. So with our conclusion, when you divide the wavelength by the fringe spacing, you get the same result for the red and green lasers. This means that the wavelength, the calculated wavelength, and the distance in the fringe spacing is the same and proportional as it goes up. The result is the higher, and then when you go down again with the wavelength, the result is lower. And then through using our equation, you can calculate the wavelength of the color of light given the fringe spacing created through using double diffraction. These are our references. Thank you for listening.